Okay, welcome everyone to panel number 4 on rain. And there's some framing language for this panel. So I'll read that. As climate change alters our physical environment, we in turn respond with adaptive modifications. This panel will open a dialogue on the relationship between climate change and the places we inhabit. How are both natural and built systems impacted by climate change? Which systems are coming under more stress? How are seemingly discrete events such as torrential rains, unprecedented heat, fires, and storm surges connected on a larger systemic scale? How have we prepared and responded in the past? And we're privileged today. Oh, I'm sorry. I just read the text for a different panel. Please bear with me. Nobody interrupted me. What does that mean? Today we are doing policy. Welcome to, no, we're on rain. Yeah, sorry. It's your fault, Wolfgang. Too many panels for me. Let's start again. I gave you good advertisement for a panel that already occurred. So unless you have a time machine, you will have to forego that opportunity. But there is recording available. So you do have that chance. We have our own little time machine built in here. So panel 4 on rain has this framing. The challenges are, how do torrential rain events place additional stress on stormwater management systems? What are some of the best practices to face these challenges? And where are similarities between New Jersey and the Ruhr region? So we have Uli Petzel from the Emscher Genossenschaft, Thomas Slautzen from the Passaic Valley Sewage Commission here in New Jersey, Carolyn Paone from Langen Engineering, Vince Masai from the New Jersey Department of Environmental Protection, Watershed and Land Management. So Uli, we're all ready for you.
Thank you very much. Big pleasure to be there to join you from Germany. A very good evening from here. Ladies and gentlemen, climate change is probably the greatest challenge currently facing mankind. It is becoming increasingly clear that in addition to technological problems, social and governance issues in particular are important bottlenecks in the socio-ecological transformation. In my presentation, I would like to take a look at the water associations in North Rhine-Westphalia and show which organizational models are being used here to exploit the opportunities offered by the water sector in the fight against climate change and for climate change adaptation. So let me briefly introduce where we are. Here you see Europe and Germany, and in Germany, the western part, North Rhine-Westphalia. And there you can see Emscher Genossenschaft and Lippe-Verband and our catchment areas. Let's have a closer look to the next slide. There you see that we are in our state 11 public water boards, all created by our role model. If you put up the next slide, please. Here you see the public water boards in North Rhine-Westphalia, where industrial companies, mining companies, and the cities are members, which is quite unusual. Next slide, here you see our catchment area. We are taking care of 4,000 square kilometers. And we're doing it with a cooperative idea, which was founded in the 19th century. Next slide. And this is a kind of democracy bottom-up. We are founded by the principles of self-help, self-administration, self-organization to ensure the freedom of our lives here. Very briefly, some economic key figures of what we are doing. We have an annual turnover of more than 500 million euro, a total balance of 6 billion euro. And we are a non-profit organization, a public water board, nowadays with 1,800 employees. Next slide. And the very next slide, there you can see our task, what we are doing, and we're doing the water management around the water cycle. That means, on the next slide, please, we try to maintain the river. We're doing renaturation, we're doing polder management, groundwater management, wastewater treatment, flood protection, waste disposal, stormwater management, climate change adaptation. We're doing everything around the water cycle. This is a wide range of tasks based on the resource of water. Very briefly look back in the past on the next slide. Our river was in former times around 1800 with a great fish fauna documented in historical Hampshire before the industrialization. The river was used for fishing and working with mills, but it didn't work very well. And then with the upcoming industrialization in the 19th century, next slide, please, the economy boomed, mainly mining and steel industry. A lot of people coming to our region. We have more than 2 million people coming here looking for work. And of course, we do not have all the logistics for those people. Next slide. There you can see what is going on. Next slide, please. And the next one, the development of our river during the 1850s to 1890s to densely populated industrial area led to an enormous increase of the quantity of wastewater. Additionally, the mining subsidence resulted in disturbances of wastewater drainage. This caused a drainage emergency, and actions were needed to be taken. And so, next slide, as a reaction to the severe situation, our Public Water Board was founded in 1899. And the big plan was the straightening, depression, and diking of the river. The Hampshire, and also the corresponding streams were regulated and concreted. The construction of an underground sewer was due to coal mining and mining subsidence impossible. Back then, the regulation of the river was the best solution. And so it worked for years and years. And here you see very iconic pictures of the old Hampshire system with the main purpose, transport of wastewater, open air, you can see. It was very efficient, but of course not sustainable for men and nature. Next slide. So some 30 years ago, the generational project started, the reconstruction of the Hampshire began. And this project comes now to an end. Next slide, please. With a budget of more than 5 billion euros, we constructed 436 kilometers of sewers. We renatured about 340 kilometers of waterways, bike passes, 4 big wastewater treatment plants. This is really one of the biggest infrastructural projects in Germany and in Europe. Next slide. In terms of its impact on the region, the Hampshire conversion is invaluable. It is an important milestone in the development from a coal and steel region to the greenest industrial region in the world, and is a role model for the further course of the social ecological transformation of our region. And the Hampshire conversion offers a number of added values for the region, which you can see on the next slide. Of course, the ecology, biodiversity is going up. It has a strong economic impact. The younger people now can learn how to live by a river. Arts and culture are supported. Next slide. Urban development really become a big issue. For example, you see here on the upper left a picture of a river and the housing area. on an old brownfield of a steel mill. Tourism becomes more important, and of course, all this is only possible if you're doing a lot of participation work with the population. For example, climate change allows us to build really a good wine at our new river. So we are prepared for the next years. Next slide. In 2027, the International Garden Exhibition will take place at the Hampshire. The bicycle mobility is a big issue here. And so as a public water board, we are doing not only what we are allowed by law, but we are really trying to be a key actor of structural change in our region. One of the big issues, next slide please, is of course climate change, the effects of which are clearly measurable. You know, of course, here the warming stripes, nothing new for you. But here in Germany, the climate protection laws in the expiring legislature were described as inadequate by the Federal Constitutional Court. With a view to the liberties of the younger sections of the population, it concludes that there is a duty to tighten up and concretize previous legislative packages. So what does all this mean for the water sector, and what contribution can it make? So here we go. Climate change challenges the water sector. Next slide. We have here in our region to take care of extreme weather events, drought, as well as heavy rainfall. Both increase. And this is only one point. On the other hand, we're talking a lot about climate justice. That means that climate justice is not only something for the rich, but it has to be an issue where even the poorer people can adapt. So exactly 3 months ago, next slide, we had here in our region the biggest floods for at least 70 years. More than 200 people were killed, and our federal government provided helps of 30 billion euros for the people. So this is really something very important. And as a water sector, we are now discussing with the government how to react. How can we prevent stormwater and floods more than ever? And the rain, which fell 3 months ago, was supposed to fall once in 1,000 years. So it was a heavy damage. And now everyone is discussing how we can handle climate change. So this means, next slide, for us as a whole, and the whole water section, as a pillar of public services and an anchor of stability and trust for citizens, that we are now, because of our attribution of competence, that we are now going to act. The water sector bears a double responsibility for climate change. As an energy-intensive sector, it itself emits large quantities of CO2. This gives rise to the task of participating in the energy turnaround and also producing as much green energy as possible itself. For example, we are now in our wastewater treatment plants at about 80% energy autark. At the same time, the element of water plays a central role in coping with the consequences of climate change. Adaptation strategies must be integrative and implemented accordingly. This means that urban planning and infrastructure construction must be done jointly with the water sector in the future to jointly develop the capacity to cope with extreme weather events. A key role in adapting cities to climate change is improving the ecological status of water bodies. It helps to increase protection against flooding and has significant positive effects on the quality of life of citizens in times of climate change. Within the scope of our water sector activities, we are the most important active environmental protector in Germany. Increasing ecological demands of our population must of course also be reflected in our work and fundamentally strengthen the interests of the water section. One example, together with our Ministry of Environment, here you see the woman on the right, our minister, we invented the climate resilient region with international appeal, and we will by 2040 decoupling 25% of all paved areas in our region. And we will increase by 10 points the evaporation in the inner cities of our cities. All this with 250 million euros until the next 10 years. And this is the equivalent of replanting more than 600,000 trees in our towns. What are we doing? Just some examples. This means, next slide, surface unsealing, water infiltration, open water separation system, drainage, ditches. Next slide, evaporation, green roof, facade greening, tree swale. This is all we can do, and we are proud as a water sector to do our job in climate change adaptation. So thank you very much for your attention.
Thank you, Uli, for a very impressive, interesting presentation. Next, we have Tom Lautzen from the Passaic Valley Sewerage Commission.
Okay. Good afternoon. My presentation's on the Passaic Valley Sewage Commission, the long-term control plan, and how we had worked with our combined sewer overflow members of our sewer district. First, just the agenda. I'm going to give you an overview of the Passaic Valley Sewage Commission. I'm then just going to give a brief review of the difference between combined versus separate sewers. Going to then just give you a little bit of characterization of our collection system and the combined sewer system within our sewer district, and then the PBSC long-term control plan that we developed with our combined sewer overflow communities. So the Passaic Valley Sewage Commission, we're located on Newark Bay in the Ironbound section of Newark. You can see the New York City skyline in the distance. We have two areas of our treatment plant. We have what we call the wet train and then the sludge train. It's approximately 140 acres treatment facility. The Passaic Valley Sewage Commission was formed in 1902 to protect the water bodies of the Hudson and the Passaic rivers. How am I turn this way? Our treatment facility, as I mentioned, is located on Newark Bay in the Ironbound section of Newark. We're the largest wastewater treatment facility in the state of New Jersey and the 5th largest in the state in the country. We serve 48 municipalities in North Jersey and parts of Bergen, Essex, Hudson, Passaic, and Union counties. We serve approximately 101.5 million residents, and we have 182 industrial discharges to our collection system. Not only do we receive waste through our sewers, we also have a robust liquid waste acceptance program where we accept non-hazardous liquids via trucked in and barged in locations. We accept approximately 350 trucks a day at 3 different discharge locations throughout our treatment facilities. Depending on what they're bringing in is where we direct them to discharge within our treatment plant. We also accept sludges and leachate versus via barges. We take in approximately 20% of all New York City DEP sludges, or 20% of all New York City sludges come our way. We also accept all the sludges from Bergen County Utilities Authority, Linden Roselle Sewage Authority, and the Passaic Valley Water Commission, which is a water treatment sludge. It's not a wastewater sludge. Our treatment facility is rated for 350 million gallons per day, but we see extremely high flows during wet weather events. During Ida, we peaked out at 800 MGD, and we averaged the day after we were putting in 462 MGD through the plant that day. And I'm proud to say we met permit. All the flow through the plant receives secondary treatment and disinfection. We have 2 outfalls. Our main outfall is into the New York City Harbor. We have a secondary outfall to Newark Bay, and all biosolids that we generate from our wastewater process is a Class A biosolids that we use as daily, that's used as beneficially reused as daily cover. So I'm just going to give a little review of the 2 different types of sewers that are out there. There's a combined sewer, which means all flow, both storm and wastewater, go down one pipe. So your wastewater out of the buildings goes into the same pipe as what all the collection system is tying into. And then you have separate systems where separate line for sewage and then separate lines for stormwater. So during dry weather events, they're pretty much seeing all flow is collected, or all flow that is generated is ending up going to the wastewater treatment facility. During a wet weather event, what happens is wastewater is still going down the same pipe. Storm drains, though, now all the stormwater is being collected. Any downspouts that are collected to that line all discharge into this common line. When this line becomes surcharged, or the wastewater treatment plant can't handle any more flow, it'll back up and discharge out through a discharge to a creek, river, or whatever it may be. Whereas with separate system, the sewage continues to go down the way it was going to the wastewater plant, and stormwater is now directed to the river. So it's separated. So you do get impacted during wet weather via sewage, via inflow and infiltration, but it's much worse when you have a combined system. So the characteristics of our system: we have a main interceptor sewer that brings the flow to our plant. It's 22 miles long. It starts up in the very north end of our sewer district and works its way down. We have a south side interceptor that comes in and brings in flow from Newark and portions of Union County. And then we have our Hudson County force main, which comes in across Newark Bay into the treatment plant and comes in just downstream of or just upstream of our primary clarifiers. And this is picking up the flow from Jersey City, Bayonne, and North Bergen. So out of our sewer district, 26% of the area is combined sewers, and the balance, or 74% of our sewer district, is separate sewers. We have 8 CSO communities throughout our sewer district, and our collection system is consistent of a bunch of flow diversion structures and CSO regulators, which are shown throughout. And there are 111 combined sewer overflows in our sewer district. We do not own any of them. They're all owned by our 8 CSO communities. So the New Jersey DEP, as part of our NJPTES permit, or the New Jersey Pollutant Discharge Elimination System permits, they require PBSC and all CSO communities to develop long-term control plans for addressing these combined sewer overflows. So they were developed to identify cost-effective solutions to the combined sewer overflows and to reduce pollution, and require an implementation schedule for these long-term control plans. The long-term control plan goal is to capture 85% of all combined sewage collected during precipitation events. We worked with our 8 CSO communities in developing these long-term control plans. We went about it with 2 different approaches. There's a regional approach where all 8 communities collectively would achieve the 85% capture. And the municipal approach is where they would all just kind of go about it on their own, doing improvements in their system to meet the 85% capture. The main differences between the two is the regional approach included a parallel interceptor that would convey the majority of the flow from the city of Newark to our treatment plant. And the way that benefited then infrastructure didn't have to be built out in the sewer district. So the selected alternative was the regional approach. As I mentioned, the main difference was the parallel interceptor and less infrastructure out into the sewer districts. Officially, the long-term control plan took 5 years to develop and put together. It was originally supposed to be submitted June 1st of 2020 because the pandemic was delayed till October 1st, 2020, and we just received comments from the DEP in June, which we just addressed the comments and resubmitted our plans in August of 2021. So once the long-term control plans are finally accepted, it's going to take 30 to 40 years to implement all the improvements out in the in these communities, with an estimated cost between 1.3 and 1.8 billion dollars when all is said and done. Some of the infrastructure that's being put in these CSO communities and at the Passaic Valley Sewage Commission is green infrastructure. Rain gardens is one of the technologies being used. Sewer separation, where we are separating the combined sewers into separate sanitary and storm sewers. Storage tanks, this would be tanks out in the system collecting and storing the flow, and when the flow subsides within the interceptor, you bleed it back in. Regulator modifications and making repairs to the regulators are out there, adding relief sewers, a secondary bypass at the Passaic Valley Sewage Commission, which I'll talk about in a minute, and a parallel interceptor. Again, that's a 5.5-mile pipeline that would convey more flow to our facility for treatment. So PBSC's contribution to the long-term control plan is we're building a bypass facility at our wastewater treatment facility. Currently we have a secondary treatment capacity of 400 MGD. What this facility will do is allow us to treat up to 720 million gallons per day. And the way it works is all flow will go through our preliminary and primary treatment. After we come out of our primary treatment, 400 million gallons will go to our secondary for secondary treatment, and then the balance, or 320 million gallons, will be bypassing the secondary treatment and then blended back in with the secondary effluent, disinfected, and then discharged both New York Harbor and Newark Bay. Any flow that goes to Newark Bay will receive dechlorination treatment via sodium bisulfite. So when all is said and done, when these programs are implemented, right now we're seeing 69% capture in our system. Within the first 5 years, we're going to see 72% capture of CSOs with some of the infrastructure. The next 5 years, we'll go from 72 to 77% capture. This is mainly going to be due to the construction of our bypass facility. In the first 20 years, which would include the construction of our parallel interceptor, we're going to a total reduction of 1.7 billion gallons of CSO overflows will be addressed, and we'll be receiving 80% capture, actually more like 82% capture within the first 20 years. Following the subsequent 20 years, we'll be collecting another 620 million gallons of CSO overflow. And when all said and done, after the 40 years improvement, we're going to see 2.3 billion gallons of CSO addressed, with an average of approximately 58 million gallons per year. That's it. Thank you.
Thank you, Tom, for a very crisp presentation. Next, we have Carolyn Payon from Carlin Engineering.
Hi, good afternoon, everyone. I'm Carolyn Payon from Carlin Engineering. I'm a civil engineer, been working at Langen for 16 years. Before that, did another small stormwater management firm, did a couple years in highway design, and took 1 year off to volunteer with Habitat for Humanity. So I was thinking, as you were talking, Tom, that if I do my job right, you have less flow. I'm working on a project right now in Jersey City, where we're under the new New Jersey stormwater management regulations, which most of my work, I work out of the Philly office of Langen, and they also have a long-term control plan. And they're, I don't know how many years into it, maybe 20 or something. But they have pretty strict, they're on the ball with their stormwater management regulations, and New Jersey has really has stepped up to the plate and made some big changes, and most notably in reducing the amount of area you can drain to any one stormwater management feature. So it's more about small scale instead of taking your whole site and draining it to one detention basin or something. And also using green infrastructure to meet all forms of the regulation, which can be more difficult and sometimes more expensive. You know, we're already our first site design. I have like 2 surface bioretention basins and 6, we're doing subsurface infiltration with, and you need pre-treatment. So we have some manufactured treatment devices. And there's also a whole set of manufactured treatment devices that are under the green infrastructure category, where they have plants. It's more of like a concentrated bioretention product. They're expensive, but they work in a pinch, and I would definitely use them. The only reason I'm not using them on this Jersey City site is because we also have a grade problem where we don't have a lot of vertical fall, and you lose like 3.5 feet over the on those devices. So let's see. So most of my projects are urban sites, like the one in Jersey City I was just telling you about. And when I was thinking of the title for today, I thought stormwater management it's not the solution to these greater storms, but it's part of the solution. And sometimes I'm very interested in the changes in the rainfall patterns and climate change and how that's going to evolve for stormwater management practitioners and engineers, and what that's going to look like. Because usually we manage stormwater from what's happening on your site existing. Okay, you're changing the land cover, you're building, you're paving over. What's the differential of stormwater depending on where you're located? Here's how you have to build stormwater management to, you know, infiltrate some of that, slow it down, clean it up, make it better. But now we're being asked, well, this site's on a river, and, you know, for Superstorm Sandy, we have another site. They flooded, you know, 6.5 feet over their site during Superstorm Sandy. And I'm saying, well, you could have the world's best stormwater management design and you're still going to be flooding during a major storm like that. But that's what we're being asked to do now. And, you know, I think the answer is thinking about how we design these sites, and certain areas, you know, realistically, depending on where you are going to get wet. So you build up, or you create those landscaped areas in the front that are designed to get wet. Or maybe you don't build there. But then it comes down to a matter of storage, right? And how much are you going to store? As a stormwater engineer, we know how much we're going to store on our site to meet the requirements. We're very good at that. But now clients and property owners are asking us, well, we want to be prepared. We don't want flooding. So what is that number? Like that site where they had all that flooding for Superstorm Sandy, they want to go above and beyond because they want to do the right thing and they don't want their site to flood. But what is that number? Is it 2 feet above what's currently required? Is it 5 feet? You know, and everything has a cost too. So we're looking at doing 2D modeling. They're right at the confluence of 2 rivers. And, you know, what would that look like? They want to build up an area that's 20 feet high, but they also know all of the other roads getting to it. Well, yeah, you may have this development that's sitting high and dry, but, you know, how are you going to get there? How are you going to access it? Plus, where's that water going to go? You can only store so much. How's that going to affect surrounding properties too? So this site is in Philadelphia, the one I have up here, and I was just wanted to show it as an example of, you know, as we move forward, there's no one answer, and any stormwater engineer now probably says, yeah, we're doing this now, but, you know, cramming in little types of green infrastructure in the site in all different places. The property line of this site, or the building, took up about 95% of our property line. So for this example, we have a big tank, that red square under the building, a big tank just for detention under the building because we just needed storage. The green little triangles are the areas of green roof on top of the building. The green area in the upper right-hand corner is a surface bioretention basin. The purple rectangle is a subsurface infiltration basin. And then there are a couple smaller things. But in Philadelphia, they want you to manage every square foot of impervious area. The requirement is to treat 1.5 inches over every square foot of impervious area. So it becomes difficult as a designer you can see around the perimeter, you may have like, you know, a set of stairs or just like a little ledge off your doorway. And you were like, well, that's bypass, you know, but they want us to treat every square foot. So we've done even like pervious stairs or like concrete stairs that slope back. And then we have a little trench drain to pick it up, and every little square foot is managed. And that's how we met in these requirements for water quality, flood control, and channel protection. Let's see. And these are just, I only have a few pictures of the completed bioretention area, but you can see it's like just tucked in, like next to that driveway. And the contractor did not install I had a really cool domed riser as an overflow designed, and I don't know what they put in, but we might go back and make them put it in. So another example, and this was something we did years ago, but I just think it's more in line of, you know, treat small, treat frequently, don't do a big basin. This is the existing Christiana Mall in Delaware. As you can see, it's a sea of asphalt. And we did a retrofit, like a facelift, that they added some restaurants around the perimeter and minimal regrading. We wanted to really limit our earth disturbance. So the requirement was to treat 1 inch over any area that was a change of use. Not that strict of a requirement. So the red areas on the right where we decided to do bioretention and bioswales, but I just thought it was interesting because we work with the existing drainage area of the parking lot. We didn't rip up the parking lot. We kept everything the same. And, you know, you have multiple design elements, and this is one photo's in construction, one's after the plant's growing. And we managed how much was getting there by the placement of those curve cuts. And it was like a back and forth just to say, okay, here's the drainage area. We're getting this much up. You're stuck to the geometry of that island. So you're getting too much, shift the curve cut so you don't get as much. And we did these, you know, throughout the mall. And that's a picture of the bioswale. They trimmed those overflow risers back. I have like couple more minutes here. So Langen and my company, I didn't work on these next two projects, but I think they're very interesting, and I think they're where we're headed for stormwater. This was in New Jersey. They used this product called Coupalex, which is like a plastic little dome, and it works in concert with concrete on top. And in this case, they provided this storage for stormwater management and additional storage for flooding, and even preparing for more frequent storms with climate change. And there's a number of products you can use for storage. And, you know, I use crushed stone a lot with fabric and perforated pipe, but then you know, if you want more void space, you can, you know, the other project under the building, we just have a concrete tank, you know, 100% void space. This product is, you know, they have like 90-something% void space, but they add that structural component with the concrete on top. I've worked with another, no, it's not a manufacturer, but it's a geostorage product, which I like because it's a concrete lid and over like stone gabions, but it provides this interior area that is 100% void space because, you know, we're looking at storage, right? So we're always looking for the products that are going to give us the most cost-effective solution. And then, you know, we start to look at the embodied carbon and which one is actually better for the environment. And this next project or series of projects, I think is really more the wave of the future. The town of Hoboken, right next to Jersey City in New Jersey, the town has these parks, and we did bioretention in there with lightweight fill, and they got a lot of storage. And there's actually a series of parks, which is interesting, but I think the most of note thing is the outlet control structures are tied to a Acti Nimbus device, which is a company that makes this, and it works in concert with the cloud and NOAA and rainfall data, and will only discharge water from the stormwater BMP when it tries to optimize, like wait till the stormwater BMP is completely at capacity and then discharge it, or if it's not, then hold it back while the storm is still going on. And with one of these, they've already seen improvements in their localized flooding. But you can see adding, they have, I think, 3 of them now in the city of Hoboken, but you can see adding multiples of those throughout the city in an area that really is prone to flooding. They're going to start to really get some benefit and have some control over when stormwater is released. Because as Tom said, a lot of the areas we work in, they're combined sewers, and every overflow that we have is not good. So, you know, I think stormwater management is part of the solution. I think you need to do your part on your site, but I think the next evolution is incorporating storage for these larger storms. And what is that going to look like? You know, who's going to pay for it? Where, how, and what material are we going to use? And things like this, how are we going to control what gets discharged at what time? Are things that I'm interested in. We're definitely looking at a lot more. That's it. Thanks.
Oh, thank you, Carolyn, for a fascinating micro level view of this problem, and also a link back to the larger scale. That was great. So our final presentation is from Vince Masai on Zoom. So it's all yours, Vince.
All right, thank you. Looks like the font got a little messed up there on this. I apologize for that. I guess one of the downsides of technology, right? But hopefully that doesn't detract from our conversation. First of all, I'm thankful to be invited. It's always a pleasure to hear about innovations that we just discussed. And you know, my role at Department of Environmental Protection, I'm a licensed professional engineer. I've been with DEP for 33 years. And for the last 1.5 years, I've been assistant commissioner over watershed and land management, which is a new program that was put together from different parts of the department that dealt with land use and also watershed protection and watershed management. And so one of the things that I always feel that DEP has done a pretty good job is looking at, over the years, is looking at site-specific impacts to the environment and having regulations that look at what the impacts are on that site. But what we haven't done well, and we're trying to now do, is to take a more of a watershed-based approach on protecting our land resources. So that means taking a step back and saying, what's the health of the watershed and what's needed here? And you know, what types of development are appropriate for it? And it's very complex, and we're working through what that looks like. But today, we're going to focus on one topic, obviously extreme precipitation, and what New Jersey's regulatory response is. So if you could just, now, do I advance the slides or, okay, there you go. Thank you. So obviously there are a number of effects of extreme precipitation, increased runoff, increased rainfall that we're getting just because of a warmer atmosphere. And, you know, I don't have to go into all the science behind that, but we obviously have a huge amount of data that shows us what the trends are. And all of this extra water means extra runoff, and extra runoff means more stream flows and more flooding. And so there's added stress placed on our aging infrastructure. Most storm sewer systems are not designed for a 100-year storm today, much less what they would be for tomorrow. And we saw with Ida that a lot of the damage that occurred was because of storm sewer systems that were just overwhelmed by the amount of water that they were asked to carry, and roads became conveyances of stormwater. And finally, because of all this extra water, this excess water that's now eventually going to get to our riverine systems, flood elevations we're finding are increasing. And the next slide shows kind of an illustration of this, kind of a real world illustration. So this is the road I live on. I live in southern Hunterdon County, and you can't see it, but off to the left, about 75 feet off the edge of the road, is a creek, a relatively large creek. And if you go to the next slide, you can see that's what it looks like in the exact same spot, the picture that I took. The one on the left was from Google Earth because the road wasn't there anymore for me to take a picture of it. The picture on the right, you can see where the road was. You can see where that tree on the right is for perspective. So everything that you saw on the left side of that road, all those trees, all that soil, everything ended up in the river. And so there are such huge water quality impairment issues that go with that. There were bridges downstream that were completely clogged up with hundreds of trees that then there was incidental flooding around those bridges. If you go to the next slide, you can see from the other end, this is where the road goes into the water now. And it happened at night, obviously, and so people didn't know, and we're very lucky it's a rural area. Otherwise, people probably would have just driven right into the river, into the creek. So if you go to the next slide, another kind of final example of this. This is standing in the creek, looking at where the road was, and you can see the retaining wall system, gabbing baskets that were put in a few years back, and they were not able to hold the road in place because the velocity was so high, and the scouring on the other side of it, behind it, was so great that the road collapsed. So we're going to see this more and more, unfortunately, as we go. And the next slide kind of shows the dynamic that's happening is that more rain leads to more stormwater runoff, right? And more runoff means increased riverine flows. And more flows in our rivers mean higher flood elevations. So if you go to the next slide, how do we address this increased stormwater runoff? Our stormwater management regulations in the state have rate reduction factors for the 2, 10, and 100-year storm based on today's precipitation, or actually based on precipitation that is published by NOAA, that is based on data from past years. And so even if you design a system that is able to convey and convey the storm flows that are anticipated for today's rain, and to convey that and to bring it safely to a stream system or the ocean, there's no way that it's going to be able to handle increased volumes. So what does that look like then? Right. So because the systems are designed for today's precipitation and not future conditions, we find that we're in a place where we need to change our regulations to adapt to that. So if you see in the next slide, so the response that we're considering right now is to say, well, when storm sewer systems are being designed or BMPs are being sized, that they not only be designed for today's precipitation in mind, but for projected future precipitation. Now, there have been a number of studies across the state that project what rainfall increases could be by the end of the century. And some reports are that the likely range of increase in precipitation in some counties could be as much as maybe 50%. So having 50% more volume or intensity of runoff is an enormous threat to our infrastructure. And the flip side of this, though, is that we could require tomorrow that all new development has no runoff. Let's say that we did that. Let's say we changed the regulation to say that's it. Anything you build, you have to infiltrate it or boil it away or something. You can't add any water to the system. Well, because of all the existing development and the existing storm sewer systems, and some areas that don't have storm sewer systems, like where I live, the runoff is uncontrolled. And so all the regulations in the world aren't going to fix that. And so we're looking for ways that we can go back in and retrofit and modify existing systems so that they can convey the storm flows, that we can get water quality treatment that's meaningful, and not just for today's conditions, but for tomorrow's. So if you could go to the next slide, please. So the obvious solution for proposed development, as I mentioned, in our mind, is to have a design that looks forward to the anticipated precipitation that will occur. So we can develop regulations that say that a storm sewer system has to be designed for today's 2, 10, and 100 and tomorrow's 2, 10, and 100 storms based on certain anticipated ranges. And of course, there's always got to be room as science changes and the data gets more refined, that we can adapt to that, which is also a challenge. The other thing too is in our existing storm water management regulations, the trigger for water quality treatment is adding a 1/4 acre of impervious surface or vehicular travel surface. So you could have situations, and I've seen this many times as the review engineer at the state for projects, where you might have 100 acres of development, and it's existing development is being removed and replaced by 99 acres of development. So there's a net decrease in impervious surface, which is of course good, But there's no requirement to treat the water quality, to provide water quality for that. And there's actually no requirement in a case like that to reduce the peak rates because the volume is being slightly reduced. So we're taking a look at that and seeing what makes sense. We don't want to discourage redevelopment. We want to provide incentives for redevelopment of our urban areas. But in the redevelopment of these areas, we're seeking ways that we can help ameliorate some of the existing problems because our stream systems, our impaired waters, the erosion, the flooding, it's not going to go away, and it's not going to get better unless we can find ways to retrofit and adapt going forward. So if you go to the next slide, please. Now, eventually all this runoff gets into riverine systems. And what we generally do in New Jersey, we either look at state DEP mapping of the floodplains or FEMA mapping. But some of these maps, like the state maps, are from the 1980s. They were based on hydrology that went back to the 50s, 60s, and 70s. And so they don't always reflect today's flood potential. And it's hard to know which maps are deviate more than others, right? After a flood event, we can calibrate it and say, we had this rainfall, we had this flow, this rainfall produced this flow, and therefore we can kind of calibrate and say, yeah, the existing mapping is relatively accurate, or it underestimates or overestimates. But absent that, there's really no way to calibrate it. And they certainly don't account for increasing precipitation because they're a snapshot in time. Now, if you look at the next slide, it shows a flood map of Lambertville. And I actually had someone in a seminar ask me why the flood line stopped in the middle of the river, as if the Pennsylvania side didn't flood. And I said, no, there's no wall there. It's just that this is the New Jersey map. And so there is a map on the Pennsylvania side. So there's a cacophony of lines here, but really what this is showing you is that the blue area is the 100-year event. And the black and white line that you can see sort of outside of that is our New Jersey flood hazard design flood. And that's based on a flood that is 25% more flow than a 100-year flood. And that was added back in 1974 by the state to state studies to account for the effects of future development on a watershed. So that predated our stormwater management regulations. But even back as far as 1974, we were seeing that reducing flood storage in our riverine systems and having additional runoff was causing flooding to get worse. So we already have this factor of safety built in, but it doesn't account for future precipitation. So if you could go to the next slide. So our NJ Pact, Protecting Against Climate Threats proposal, which we're working on right now, which would include the flood hazard rules, the freshwater wetlands rules, the coastal zone management rules, and then shortly to follow the stormwater management rules. The thinking and what we're developing right now are rules that would require buildings and infrastructure to be designed to future fluvial flood elevations. And so what that looks like is, and this is where it becomes very difficult. We know that there's more rain coming. We know that more rain is going to produce more runoff, but it's not a direct relationship. 20% more rain does not equate to 20% more runoff. It might be more, it might be less, depending on the ground conditions and the systems that are in place. 20% more runoff does not equate to 20% more flow in a peak flow in a river, right? Depending on the timing of it and the watershed size and a number of other factors, it could be more or less than that. And an increase of 20%, let's say, in a riverine system of flow does not equate to a 20% increase in flood elevations. So there are a lot of dynamics that are going on here hydrologically and hydraulically. But what we do know is that more rain means more flooding. And more flooding means that people that are building to today's standards might not be protected fully for tomorrow's flood. And what we're finding is that new development, when you build higher and when you build in a more resilient manner, that it actually saves money in the long run. A good example is a home. If you build a home to the base flood elevation today, your flood insurance rate will be a certain amount. If you build it 1 foot higher, the lowest floor of your building 1 foot higher than the base flood elevation, then you have a savings in your flood insurance. And the higher you go, the more savings you get. And we found that in most cases that we studied, that the added cost of building higher upfront, that you made back all of that investment within 4 to 6 years, just in flood insurance savings. And not only was the structure much more resilient to flooding because it's higher, and so therefore, if the flood maps are inaccurate in a given area, because the flood doesn't know it's supposed to stop at that line, and we saw that in Ida in many cases, and during Sandy. But so not only is it more resilient and you have a better factor of safety, but for the lifetime of the structure, I think the average was that during a 30-year mortgage, that the average structure, if it were 3 feet higher than the base flood elevation, would save like $75,000 in flood insurance rates based on today's rates. So there's really kind of a no downside to it, except that upfront there's going to be some incremental cost to build more resiliently. Now, sometimes people are going to be in situations where there is no flood map, and that happens a lot today. And so what we would do there is we would say, if you calculate the floodplain, we calculate it based on this anticipated future 100-year flood based on projected precipitation, and we're calling that the climate adjusted flood elevation. So we have one set in New Jersey. Most likely, I would say at this point, it looks like we would be raising the flood elevation of 1 foot in fluvial areas, maybe 2. We're trying to kind of pare down on the data to see what the best balance is. So right now, in general terms, our design flood is about 1 foot higher than the BFE. And if you can go to the next slide, please, you can see that. Thank you. So if you're using the mapping, right? So today's flood elevations, our design flood across the state is always about 1 foot higher than FEMA. Sometimes it's more, but it's always at least 1 foot higher than FEMA's BFE. And the floor of your buildings and the surfaces of your roads, where possible, need to be elevated or flood-proofed up to 1 foot above that. And you can go to the next slide, please, because that's actually where that's listed. And so what ends up happening if we bump up the flood elevation 1 foot, and then we have 1 foot of freeboard on top of that, then that means that the floor elevation of buildings would need to be either elevated or flood-proofed, flood-resistant, up to 1 foot above that climate-adjusted flood elevation, which would be roughly about 3 feet above the base flood elevation. And obviously, that's for riverine systems. Along the coastal systems where sea level rises, the dynamic, then it's a different measurement. So that's really just kind of a cross section of where we are. We're in the process of. You can go to the next slide if you'd like. We're in the process of fine tuning what the regulations look like. We're hoping that by the end of the year that we would propose a comprehensive package that would include these and other changes. And what would follow then is a comment period, 60-day comment period, and a response to comment. And so our vision is that by sometime in late 2022, we would have new regulations in place that would account for increases in precipitation. So that's my presentation. Thank you. Feel free to email me if you have any questions.
Okay, thank you, Vince. Thank you for that excellent view from the state level perspective. We now have some time for Q&A, both from Zoom and from the live audience. And right now I see there's one question in the Zoom chat, which I'll come to in a sec, but let me see if there's any questions from the live audience for the panelists. Go ahead, Wolfram.
So, well, thank you so much for these insightful presentations. And actually, my first question, when we heard so much about these extreme flooding events, and we heard all those pictures. My first question actually goes to Uli and your presentation. And if you could talk a little bit, explain a little bit, how did this extreme flooding that happened this summer actually impacted the MSHA system? Because that's kind of thing I would be interested, because you were Carolyn, you were talking about that you built for these extreme situations. Uli, you are dealing with a 150 years old system. So my question was, how did this old system actually deal with these new challenges?
I can answer this if you want to, Wolfram. By law, we have to build a river system for 100-year flooding. What we did with the Emscher system is for a 200-year flood. And fortunately, the heavy rains in our system were 200-year rains. So our system worked very well. We had nearly no problems. But suppose the rain from the region where the heavy floods took place fell in our region, our system would not have be able to protect the people. We would have damages of about 7 billion euro. So we know that we have to do more to build up dikes, to do technical things, retention bassins, whatever. But everyone in our region now knows that he or she has to protect her house by herself first. So this will be the key issue. We have a very large discussion in Germany, in our region, everywhere. What can I do for myself? And what have I to do for my neighbor? What about the government? What can the government do? What about insurances? So this is a very vast discussion nowadays here.
Thanks, Uli. There's a specific question in the chat for Tom, which is what percentage of the LTCP is green infrastructure in terms of investment or stormwater management capacity?
Dollar wise, don't know what the value is out of the 1.3 to 1.8 billion. For total, I believe it's on the 5 to 10% range of the projects that are going to be constructed or in the green infrastructure.
And percent of projects or percent of capacity?
Oh, projects. Presented capacity. I don't know the number off the top of my head of how much of the reduction is going to be associated with green infrastructure.
Okay, thanks, Tom. Other questions from the audience? I don't have any others on the Zoom chat at the moment. Are there any others from the people in this room? Well, I have a couple of general questions that I'd like to ask all the panelists, all four of you. I'd like you to say a little bit about the obstacles that your work has confronted. I mean, you've talked for the most part about what you are doing and what you're planning to do, and in the background are various obstacles that I'm sure you're grappling with. That they may be political or economic, or they may center on certain actors or certain institutions or certain kinds of relationships. But whatever comes to mind in terms of the main obstacles that you confront, and if possible, what you have been able to do to overcome those obstacles, or what you think is needed, what kind of resources or other factors that you would need in order to overcome those obstacles. So anyone can go first. Vince or Carolyn, we haven't heard from you yet.
Go ahead, Vince.
Hey, how's it going? After you.
Okay. I mean, my obstacles as a designer are just that, land is expensive, and sometimes even what I want to do in terms of green infrastructure isn't even possible because we're designing a warehouse and you can't do certain things because the truck's turning, and so we can't do porous pavements. Or I'm not saying there aren't things you can do, and we're creative about it, but like the Jersey City site I'm working on, once the building is in the middle and then we got truck parking on either side and the driveways, and they've crammed as much as they can on the site. There's a couple little triangles for stormwater, and maybe they're on the uphill side, and so that's it. And but I think just to, to be able to do more of what I want to do, it helps me personally when the regulations shift, because I'm like, well, we have to do this. We need to squeeze in more bioretention. We're going to have to redesign the site. So having the regulations really catch up with what I would like to see just personally, I think helps me.
Okay, good. Thanks, Carolyn.
For our challenges is financial. The price tag is 1.3 to 1.8 billion dollars. Several of the communities are environmental justice communities. So, when they're facing hundreds of millions of dollars in capital costs over the next 30 to 40 years, it's a lot of money that that has to be found to finance these projects. So it's financial is the biggest challenge.
Right. And what are the alternatives that are being discussed? Or
We're looking to finance through the New Jersey Environmental Infrastructure Bank, but we're also looking for grants. We're trying to go to the federal level to get money through the federal level to finance these projects. So we're sofa cushions anywhere we can look for money is where we're trying to find it. So mostly trying to find some grants and low interest loans.
okay, good, thanks. Uli, Vince?
Carolyn is so right. We need a new kind of urban planning. This is our main obstacle. We are now discussing with the cities in our region by the behalf of a sort of building law that the city council can vote that every new house built has to have a green roof or a green facade, that they have to do decoupling. We're discussing a sort of obligation for every landlord, for everyone, for every investor, for every enterprise. So this will be very difficult to do, but most mayors and most politicians think that this is the only way to achieve blue-green infrastructure adapted to climate change.
Okay, thanks. Vince?
And thank you. So as a regulator, my challenges are sort of on the other side of the coin, but obviously it's the same issue. Our goal, all of us, no matter whether we're regulated or regulator or regulatee, is we want people to be safe. We want storm management systems to function properly. We want stormwater management. We want to be protected against flooding. And the challenge as a developing regulations is can we adopt regulations that are achievable, because we could have such extreme standards that they're just unachievable, and then everybody needs a waiver from that, and that's not good rulemaking. Does it consider all of the variables, which again we're kind of getting better at, but there's just so many things, even with the current stormwater, the GI green infrastructure rules that were adopted and became effective in March of this year. There are things that we anticipated that haven't happened, and there's designs that we didn't anticipate that are happening, and so we're trying to adapt to that and come up with guidance for that. But really, it's a serious thing that our Flood Hazard Area Control Act rules, the Act and the Stormwater Management Acts, that they mandate that the state adopt standards that protect people to the extent they can. And so it's a very sobering place for us to be, because we don't want to discourage redevelopment. We don't want to discourage development, but we want it to be safe. We want it to be resilient. And so reaching that balance is very, very difficult. And we're going to miss the mark in some places, but I do feel confident that we'll get to a place that's achievable and protected.
Okay, good. Thanks, Vince. There's a question from a Zoom participant, Carol Stein, also for you, Vince. She writes, regarding the flooding due to Hurricane Ida on September 1st, much of this flooding was in basements of homes and apartments that were not considered to be flood prone. Are there any plans to have regulations limiting construction of dwellings in basements? Or are there other plans to help prevent this scenario from occurring in the future?
Yeah, that's a great question. So yes, some of the basement flooding that we saw was people that were in the floodplain already mapped or just outside of it. And as floodplains are increasing, there are folks in this fringe around the existing floodplain that I feel are particularly in danger, because you could today build a home with a basement right outside the flood hazard limit, and there's no regulation that says you can't do that. One of the benefits of having a larger floodplain as a future floodplain design is that it would incorporate some of these people that are right on the edges. Because under the regulations today, if you're in a flood hazard area, you can't have a basement. Your lowest finished floor has to be 1 foot above the design flood elevation, or if it's commercial, you can floodproof it, but you can't have basements. But for those folks that are far away from the areas that we regulate, and it was mostly stormwater driven in those areas, and there really isn't anything we can do under the flood hazard rules to say no basements. I think that's probably going to be a market driven thing where basements, if they're perceived as being flooded frequently, are going to be less desirable for homeowners. And so I can see a change maybe in the construction patterns, but even still, we've got tens or hundreds of thousands of people with basements that share this. You know, my home is not in a flood zone, but I got water in my basement just from groundwater coming through during Ida. So, you know, that's unfortunately the new normal that we have to deal with.
Thanks. Other questions from the in-person audience? Then if not, I have another general one for all the panelists, which is, what lesson do you think you could take away from your experience in your jurisdiction that others elsewhere might benefit from? I'm not asking you to necessarily leap across the Atlantic with your recommendations, although if you want to, that would be great. But just thinking about other places other than where you've been working, where you think that you've learned something that's generalizable. Want to start maybe again with the on-stage folks here with Carolyn and Tom?
So I got involved with our long-term control plan at the very tail end. I've only been with PBSC for a year and a half, so it's hard for me to say, but I think something that I've learned is you gotta working together is critical, as opposed, we talked about the regional approach, the municipal approach, working together to come up with a solution with 8 CSO communities and collectively come up with a way to address the issue is much more efficient, much more cost effective, and better for all than divide and go about it separately. So I think that the team approach is the right way to go about resolving problems. So I think it's a lesson learned, and it's probably the best way to go about that.
Great. Yeah, maybe Uli can also comment on that issue in the German context. Carolyn?
I think recently I organized we've trying to get more education with our sustainability group at Langen. So we have a series of design trainings, and I organized one for stormwater management, and I purposely sought out people from different geographic areas, and I was shocked how different stormwater management is in Phoenix compared to here in Texas and in Florida. And I think sometimes as designers, you get in your head with, well, of course, everything's due yesterday, but you have certain things that work, right? And if you were designing in the 70s or even the 80s, you did a detention basin with a low flow channel, and it was hard to change that, but so I think having more education and more, like, even for myself to hear what other people are doing, like my counterparts in New York City, they do the blue roofs, the storage of the stormwater on the buildings all the time because they have to. They're in New York City. They're either under the building or they're on top of the building, and for the most part, or doing reuse. And even just as far as Philadelphia, we always bring it up as an idea, and everyone's sort of like, oh, I don't know about that. Let's try something else. But having more exposure to different ideas and getting that comfort level, then you can probably come up with a better solution if you're more comfortable saying, you know what, let's try this because what we normally do isn't working for this site. And let's, we had like a FedEx facility, and we couldn't infiltrate. We had I don't know, all sorts of environmental and bad soils but we had to meet the requirements. We ended up doing 8 acres of bioretention. It was only ponding 1 inch with a lined system. And then we still needed, so we ended up doing water reuse for the trucks, and we're I'm assuming every truck is getting washed once a week over there. So I don't know if it's happening, but but having to think outside the box. And I keep trying to, learn more things myself too, so that you have, when you're in a tight site with new regulations, and you can try to come up with a better solution.
Good. Yeah, great. Thanks, Carolyn. Vince or Uli?
Thank you. So I would say, our stormwater management regulations are based on a lot of assumptions, right? For example, the rate reductions, the 2, 10, and 100-year rate reductions, based on studies that were done in some.
I'm having trouble hearing you, Vincent. Can you closer to the mic?
That's interesting. This is my mic, so that's about as close as I can get. Can you hear me?
We lost you again.
Can you hear me now?
You were very faint, and now you're gone.
Oh, not sure.
Try talking, Vince.
Hello?
Great.
You can hear me now. Okay. All right. Thank you. I'm sure I said something wonderful, and I can't remember what it was now.
It was terrific, but say it again.
It was amazing. I was very, yeah. Our stormwater management regulations are based on certain assumptions, and they don't take into account where you are in the watershed. So you can have situations where you're at the very downstream end of a watershed, and maybe there's no particular reason for you to have to retain the volume of water that you're retaining. It might be better just to get it out before the rush comes. Maybe in other parts of the watershed, it needs to be detained even more because of the timing of it and the size of the size of the drainage area and the time to peak and whatnot. So I would like to see us develop more regional stormwater management plans for watersheds, because I think that within that, then we can help guide how development will happen and say, here's the areas that will have the least impact on the watershed. And so we don't need to have as stringent standards for volumetric reductions or rate reductions. And over here, however, this is the area that we want to set aside to maybe recharge more or whatnot. So I'd like to see that instead of a one-size-fits-all approach that we take now.
Vince, I know Philadelphia has that. If you're geographically, they have it mapped. If you're in a conditional district next to the Delaware or the Schuylkill, you can dump it in, and then you're further out, you're holding it back longer.
Right, exactly. That's the kind of thing that I think I'd like to see in New Jersey. Yeah.
Uli?
I think that it is very important to work together, and climate change adaptation can't be done by one city or one sewage commission or a public water board. We can only do it together. And so maybe the idea of a public entity which is responsible for working together could be a good idea. And this is what we are discussing now with the government, that we as a public water board get this new task for doing climate change adaptation for the whole region. So this could be a good idea in other countries too.
Good, thanks. I want to have two last questions, a little more specific, one for Uli and one for Vince. So about the Emscher Genossenschaft and what you describe as the Emscher conversion, it was in your talk, sort of in the middle, and it went by a little quickly, and it seemed like, it's maybe the biggest and most inspiring thing about your case. And could you say a little bit more about how the Emscher conversion came about? What were the forces, the actors who were behind it? A little more details about when it occurred, how much it cost, things like that.
Mm-hmm. The idea of the energy conversion came up in the 80s. A new ecological consciousness came up in Germany, and the idea of open air sewers was no longer a sustainable idea. And so everyone said, well, you have to check now if it is possible to build proper sewers and to do the renaturation of rivers. So we made a plan in the end of 80s, beginning of 90s, and we said, okay, it is possible. It will take 30 years and it will cost 5 billion euro. And so the region, the coal mining industry, everyone said, okay, go on, just do it. And so we did, and we are in time. Finally, it will cost about 5.5 billion euro, 10% plus in 30 years is, from my point of view, not that bad. We created 4 big decentral wastewater plants. 2 are among the 5 biggest in Germany. 340 kilometers of new waterways, 200 kilometers of cyclable pathways, a lot of added value for the region. And this is really a project supported by the population, the politics, the industry. Everyone said, well, if we want to have a chance and to be competitive in the next decades, we have to change from gray to green blue. And this is the idea for our region.
So it sounds like part of the solution really was to spread the spending out over a long period of time.
Yeah.
Could you say a little more about the financing? Was this general revenue, was special fees? Was there bonding?
Well, that's not that easy to explain. The invest was financed by the European Investment Bank with a very good interest. So we have a very good stability in financing. They gave us the money for 45 years with fixed interest, very low rates. And the industry, the coal mining companies, the cities has to pay every year amount to us, to our public company. And the cities then take the money from the people for the task of putting wastewater and cleaning wastewater, etc. So this is a very stable financing case. There is even special law, more than 100 years old, for this financing.
Okay, great, thanks, Uli. Very interesting. And I have last question for Vince about your work, creating this new regulatory framework, which is challenging, but also in a way kind of exciting that you're sort of I guess a relatively new area for the state, or it's an updating of where the state has been active before. And I'm just wondering if you could say something about where you're getting your reform ideas from. What other sources, are there any other jurisdictions that have good approaches that you're trying to learn from? Are you learning from academic work? Or are you learning from from the state's own history? Are you in consultation with stakeholders? What does the process look like? And also just what are the areas where you're finding really the most interesting new ideas?
All of the above. That was a great list of sources, because that's exactly what we've done. We have, of course, academia providing us with data that suggests the direction that we should go. Then generally speaking, we would develop some ideas internally we would look at what neighboring states do, especially in the Mid-Atlantic states, areas that have the same type of hydrologic patterns that we have, and see what works for them. And we have conversations across the borders with Pennsylvania and New York a lot. And then what we do is we stakeholder our ideas, and we put it out to developers and engineers and designers and end users, and say, here's the issue that we're trying to tackle. Here's what the science says. Here's our intended direction. What do you think? Does this work? Does it not work? Is there a way to improve it? And then we go back and forth a bit through that process and fine tune our approach to regulations. And then ultimately, when we're comfortable that the goals have been met and everyone's been heard, then we propose it. And then, of course, the proposal period is an opportunity for everybody to write in and say what they like and don't like about it. The flood hazard rules in 2007 that I authored had 1,023 comments. So every one of those comments need to be addressed. And some of those comments led to changing some things in the rules, because some things that we thought would work, we realized wouldn't work. And things that we needed to address later, we took out and addressed later. So it's really all of those things that you mentioned.
Okay, well, great. Thanks, Vince. I think that we're done with the content. I want to just thank everyone for coming, the panelists, both on stage and online, the audience in the room and the audience on Zoom, and the tech crew, which keeps everything running smoothly, and Wolfgang for organizing the conference. Thank you all.
Thank you so much.
Well, thank you for myself, totally to you. And two things. One thing is, even if the room looks more or less empty, the thing is that, number one, we had online audience, and this is all recorded, so we're gonna keep it on. And also that our whole approach of finding, continuing this into a publication, will that we translate this discussion. And it was very much like a very interesting workshop, I think, this afternoon. So I really appreciate that. And the second thing is we will have our closing comments that Frank Gallagher is going to do right in a few minutes, right in here. So thank you all. Thank you.